Hi, today I'd like to go over a geometry problem which I saw recently and that caught my interest in certain ways. So it is as stated on the screen. If we have a circle which is inscribed inside of a quarter circle as in the image below, and if the radius of the small circle is 8 and the distance from the point E to the point B is 10, then what is the radius of the quarter circle that we see in the image? This problem is taken from the 2024 edition of Pythagoras Quest, which is a Swedish math competition for high-achieving middle school students. So basically what this means is that you need sort of a working knowledge of geometry, you need to know some basic theorems about Euclidean geometry, including how to calculate areas of circles, you need to know how to compute, say, the hypotenuse of a right-angled triangle, you need to know about similarities, you need to know about angle sums, and so on and so forth. A lot of these basic theorems from Euclidean geometry. If you'd like to have a go at this problem, feel free to pause the video. So, to solve this problem, there are a few things we need to note, and one of these things is not that easy and is what I suspect that most people solving this will not have managed to do. But let's begin by taking in the simple stuff. Let us see what we can do with ease. For instance, what is the distance from D to E? How long is this line segment? Well, this one is pretty simple. We see that the radius of the small circle is 8, and this line segment from D to E is simply that radius, so it has to be 8. Likewise, we know that the distance from this point E to the point B is 10, as stated in the problem description. We also know that if we can compute the distance from A to E, then this distance from A to E plus the distance from E to B must be the distance from A to B, which is the radius of this quarter circle here. So this is what we want to compute, and I will call this distance x. Now, to compute x, we need to find some way to express this in an algebraic equation. And the way we will do this is to construct this line segment from A to D, which makes a right triangle, ADE, with the right angle at E. Now, it's not so simple to know how we express this hypotenuse algebraically, but if we could do that somehow, then we can just write up an equation using the Pythagorean theorem, and maybe we can solve for x that way. Now, in order to find the equation we need to solve for x in this setup, we need to make the following observation. If I add this point I to the image below, then I can add a circular arc as follows. And now the question is, what good is this anyway? What can we do with this that we couldn't before? Well, I will make the following claim, that the distance from I to B is equal to 8, which means that the distance from E to I is actually equal to 2. Which means, by extension, that the distance from A to D, which is the radius of this circular arc, must be the same as the distance from A to I. So the distance from A to D must be x plus 2. And now we can construct our Pythagorean theorem equation from this using x plus 2, 8, and x. But the question is, how can we actually say that this distance from E to I is equal to 2? Well, that actually has to do with what happens if we extend the line from A to D all the way to a point F up here. And then we get this line here. Now, what we see is that the distance from D to F is actually, once again, the radius of the smaller circle. So the distance from D to F will be 8. And this distance has to be the same as the distance from I to B because of this construction that we made. So we know that the distance from I to B is 8, and we know that the distance from E to B is 10. So we get that the difference between these distances is 2, which is why we can write that down. And now we can simply solve this equation that we get from Pythagorean theorem, which is that x plus 2 squared is equal to x squared plus 8 squared. And now I won't really draw out equivalence arrows or anything like that, just every step on a new row. So if we expand x plus 2 squared, we get x squared plus 4x plus 4. And here we still have x squared, and 8 squared is just equal to 64. And now we see that x2 terms on both sides just cancel out, and we're left with 4x plus 4 is equal to 64. Now subtract 4 from both sides, and we end up with 4x is equal to 60. And now if we divide both sides by 4, we get that x is equal to 60 divided by 4, which we can compute to be 50. And from this, we can now just note that the radius that we're after is equal to x plus 10, which is just 15 plus 10, and is equal to 25. So, why do I want to look at this problem? What is it that makes it interesting to me? Well, first off, when I first looked at this problem, it took me actually a while to solve it. It did not come naturally to me at all to make this inner circle arc from A to D to I. And secondly, when I was looking for a solution posted online, I didn't find anything. And this is quite baffling to me. There was an answer. The answer 25 was there, but there was no solution posted online, which to me is just inexplicable. You have all of the resources to do this. You obviously know how to solve the problem. So why not post how to solve the problem online where you post it to begin with? I mean, isn't this supposed to be a resource for kids to learn how to problem solve effectively? And if they can't do it, what are they going to turn to? Someone who knows to solve the problem? Well, who is that supposed to be? This is not a simple problem. Even if it looks simple, if you hit upon the right idea, if you don't realize that you have to look at this circle arc from D to I, I'm not sure you can even solve the problem in the first place. You know, when I started looking at this problem, it wasn't that I just drew the circle arc intuitively and thought, this will help me out greatly. Of course it will. Obviously, I'm not going to have any problem here. No. Instead, I was in the situation where I had this picture up, but I hadn't realized that I should have x plus 2 here. I hadn't realized that the distance between E and I was 2. I didn't even realize I should have a point I to begin with. And I didn't really know why I was supposed to draw this circular arc at that place. In fact, the first time you see this problem, it's not clear at all what you're supposed to do. And there are many things that you don't quite know for sure are true. For instance, can we even say for sure that when I extend this line segment from A to D, I will get a line segment from A to F here, where F is actually the point of tangency between the inner and the outer circle? It's not clear at all from the beginning, but it's not that difficult to prove. So basically what we need in order to prove it is to realize that since this line segment from A to D goes through the center of the circle, then its extension will basically go through the diameter of this circle. So if we reflect this inner circle across this line segment, then it will be reflected on itself. And basically what we do is that we take this circle sector AFB and reflect it across the line segment AF. And what we get is the following image. We get a point B prime and this line segment here, and then we get this point E prime of tangency. And we realize that, well, this has to be a circle sector, and this has to be a circle sector, and they have to have the symmetry, and the only way we have the symmetry and we have that this circle inside is reflected upon itself is if this point is actually a tangent point. Because if we had something slightly to the left or slightly to the right, then this circle would not be perfectly preserved in this way. So that's pretty easy to realize that yes, in fact, this line segment here actually does intersect the outer circle at the point of tangency. So that much is clear. But from here, where do we actually go? How do we realize that we need to draw this circular arc? Well, at first I didn't do that at all. At first I thought about maybe using similarities instead. And I thought, what if I draw a line down from F that is parallel with DE in the following way? Let me see if I can find it like this, and get a point of intersection at J right around here on the line segment from A to B. And then if I can somehow maybe get this distance from J to B, and maybe I draw a line segment from D that is orthogonal to this line segment FJ, I get something like this, and I get this point of intersection H. And then I have this right angle triangle at DHF that is similar to the triangle AED, and also similar to the triangle AJF. And maybe if I can mark these distances as A from D to H, and the distance from H to F as B, then if I can compute A and B somehow, then I can just say, using similarity, that x divided by 8 must be equal to A divided by B. Now, what I quickly realized using this idea was that it's very difficult to figure out what A and B are based on this image. And the fact of the matter is that it's actually possible to do this, but only if you draw the necessary circle arc. There is no other way that I've found to get these distances. Even if we know 8 and 10 here, there was no other way for me to really crack how to get these distances A and B. Basically, what you can do if you also draw in the necessary circle arc as follows, and then you have that the distance here is 2, then what you realize is, and I will also add this point I. So what you can do then is to realize that the shape DEI and the shape FJB are actually also similar. So the quotient 8 divided by 2 is equal to the quotient of F to J divided by the distance from J to B. So basically what this gives you is an equation which looks like the following. You get that the distance from F to J, which is B plus 8, is actually equal to 8 divided by 2 times this distance here. So it's basically 4 times 10 minus A. And when you use this together with the fact that A squared plus B squared is equal to this distance squared, then we also have that A squared plus B squared is equal to 8 squared. And when we use this, we can use these two equations to get a relationship between these two and somehow simplify a lot. Basically what we do is we move this guy over to that side, then we can use the rule of conjugates to factor out B plus 8 from the expression, replace it by this guy here, and then we solve it. But procedurally it's a lot more difficult than what I showed you at the beginning of the video using Pythagoras theorem. But to me it's interesting that you can solve it in multiple ways, although all the ways I've found so far actually do require us to realize that we need this distance between E and I. We need this circular arc. Otherwise, I can't see how to solve the problem at all. Now, with all this being said, I have this sort of love-hate relationship with these geometry problems, because on the one hand, they are kind of fun and they are not procedurally that difficult to solve if you hit upon the right idea. But if you don't hit upon the key idea, they are basically impossible to solve. And that's why I sort of like them and I dislike them a lot. And they bring me so much frustration when I work with them. And still, to me, it's such an inexplicable decision not to have posted the solution. Because if you don't realize that this circle arc from D to I has to be drawn in, then you're not going to solve the problem. You're not going to have any idea how to arrive at the conclusion that x equals 15. And to me, that is just absurd. And what I would like to do in the future maybe is to sort of make a compilation of different kind of these problems and talk about them more in depth. Because oftentimes when I see solutions to these kinds of problems online, what I feel is that they don't really account for how difficult they are to solve and how easy it is to get stuck without any way forward. And what I'd like to do is basically be able to showcase how even if we can solve a problem easily once we hit upon the right idea, it's not that simple when we don't know how to solve the problem to begin with. And the arduous journey to realizing how that we need to draw this line, this circular arc out. Now, I'm not sure exactly how I will be doing this, at which level I will be doing these solutions and reflections, but it is something I've thought about a lot now and that I think is a really valuable resource that is sort of missing. Not because people aren't posting solutions, but because they're not really taking seriously how difficult these kinds of problems can be. And that's, in my opinion, a shame, because I think many more people could enjoy problem solving a lot more if they realized it isn't as easy as it looks, and they're not as stupid as they think they are for not hitting upon the right idea by some basically stroke of luck. Now, I don't really have much more to say today. I wanted to post a video about this problem just to vent. If you have any comments, feel free to post them, but otherwise I will be checking out for now. Thanks for watching, and take care. Goodbye.